Hello and welcome to the NPTEL MOOC on Applied Electromagnetics for Engineers. We are in the last few modules of the transmission line theory that we have been discussing. In the previous module we were discussing the time domain behavior of the transmission line, where the source impedance was in general not equal to the characteristic impedance, and the characteristic impedance of the transmission line was not equal to the load impedance. This resulted in multiple reflections with the output approaching the steady state value in an asymptotic manner. That is, it does not approach in a single time duration what would be the final value or the steady state value, but it approaches in a series of staircases or ring kind of a approach. So it's the transient response that we were interested in. In this module we will consider a general type of a termination. Specifically, we will be interested in those terminations which present capacitive or inductive type of loads for the rest of the transmission line circuit. We will see that the concept of reflection coefficient and the lattice diagram that we studied in the last module will not be directly applicable here, because the reflected voltages will not be, or reflected currents will not be in the same shape as the incident voltage and the current. Both reflected voltage and the reflected current will be functions of time even when the incident voltages are not functions of time, or they are constant with respect to time. Okay. So we will see how to solve such problems. We will consider the simplest case of an inductive termination first, then go to capacitive termination. So what is the problem that we are discussing? Remember, we had a source somewhere, right? This source we had considered it to be a step kind of a source. We were considering the idealized step voltages. The amplitude of the step voltage, let us say, is equal to V0, and this was connected via a resistance or the internal impedance of the source, which we called as Rg. In the previous module we let Rg to be whatever the value it was, and therefore there was reflections at the generator side as well. However, to consider that approach with reactive terminations will be little complicated. One has to perform Laplace transform on the signals, on the functions that we are considering in order to solve those problems where Rg is in general different from Z0. So what we do instead is to assume that Rg is equal to the characteristic impedance of the transmission line, which immediately means gamma g is equal to 0, and therefore there is no reflection. When the reflected voltage comes from the load traveling towards the generator, there won't be further reflections from the generator side. As before, we will turn on this transmission line circuit or the source. So we will turn on this source at a time t equal to 0, okay, connecting to the rest of the transmission line, which will have a characteristic impedance of Z0 and a time delay, one-way propagation time delay of Td, which comes because of the propagation length L of the transmission line, and the velocity of the wave, voltage wave on this one, will be given by the velocity u, not up, velocity u. Okay. So we connect this transmission line to a reactance. As I said, we will consider first the case of a pure inductance. We label the voltage across the inductance as V subscript L of t. Please note that this subscript L does not denote inductor, okay, because later when we consider the load to be a capacitor, we again label the voltage across a capacitor as VL of t, okay, and the current through the capacitor as IL of t, indicating load. Okay, so these are not indicating the inductances, they are simply indicating that this is actually a load voltage. So as I said, there will be a current through the inductor which we will label as IL of t. At any point on the transmission line circuit, right, at any point on the plane on this transmission line circuit, there will be some, line voltage, and this line voltage at any point on the transmission line, or because of the continuity, must be equal to the load voltage at the load side. We can choose Z equal to 0 as the source and Z equal to L as the load, or we can choose Z equal to 0 as the source and then Z equal to minus L as the generator. Doesn't really matter which one we choose. Let us arbitrarily go with this coordinate representation. So Z equal to 0 denotes the sending end or the generator, Z equal to L denotes the load. So there is a certain line voltage which we recognize must be composed of the incident voltage, which is changing along the line, plus the reflected voltage, which is V minus of Z comma t. So this is in general the line voltage. Okay, so we have seen these expressions right from our second or third module where we were discussing the line voltage. Similarly, we will have the line current as well. The line current again will have both incident current as well as the reflected current. This line current will also be changing along the length. Okay, what is the incident voltage at this point, or rather what is the incident voltage V plus? Let us look at the circuit here. Before the switch is closed, that is for t less than 0, we assume that the entire circuit is not energized, which means there are no initial currents or no initial voltages at any point on the transmission line. So at t equal to 0, when we turn on the switch, the generator has still not seen the load here. The load is invisible to the generator. This is because this first an incident voltage has to go, get reflected and then come back, right? Only when it comes back, then the load, which is inductor, capacitor, or it could be anything, that becomes visible to the source here. So we have an amplitude of V0, there is an internal resistance of Rg. So as far as the source is concerned, at time t equal to 0, you actually see the characteristic impedance of the transmission line as the input impedance. So the impedance seen looking into the input terminals of the transmission line will appear as the characteristic impedance Z0, because that is what the source can actually see at t equal to 0. Consequently, it will generate an incident voltage which we will label as V plus. So at the source side it would be V plus of 0 comma t, which would be V0 divided equally between Z0 and Rg. In this case we have considered Rg to be equal to Z0, therefore the voltage amplitude will be V0 by 2. However, please note that we can consider the switching action. So this was the switch action, right? The action of the switch is to connect the generator to the rest of the transmission line at t equal to 0. We can model that reaction by modifying the voltage source as V0 u of t, where u of t is a unit step function, okay, which will be 0 initially for t less than 0. So if you plot this as a function of time, this would be 0 initially and it would have an amplitude of 1. So obviously multiplying this unit step function by a voltage V0, we get the step voltage. So what we actually launch as the initial voltage V plus at the generator side is actually V0 by 2 times u of t. Let us further introduce a simple, or rather simplified constant. Instead of carrying this V0 by 2 all the time, let us call this as V plus. V plus denotes the amplitude of the initially launched voltage. If you remember our the lattice diagram, this step is similar to the first lattice diagram where we were calculating V1 plus. So fortunately that step is still the same. However, the rest of the step will not be the same, okay, and instead of V1 plus we call it as V plus, because we know that there will only be single reflection. So this V plus goes all the way to the load, and from the load gets reflected and comes back to the generator and will be absorbed later on. So V1 plus would travel, V1 minus would reflect back, okay. However, V1 minus will be in general not equal to some constant times V1 plus of t, okay. So it won't be exactly of the same shape, just changed in the amplitude, whether it is positive or negative amplitude change. It will not be equal to the incident voltage, it will be different from the incident voltage. However, once it comes back at a time 2 times Td, this would be completely absorbed. There won't be further reflections from the generator end. To summarize, at t equal to 0, we launch a voltage whose amplitude is, let's say, V plus, and it is u of t that we have launched. At what time does this initial incident voltage reach the load? It will reach the load after a time t equal to Td. Thus at time t equal to Td, this voltage would have reached, which is having an amplitude of V0 by 2, right. So this voltage reaches the load side, so which means any operation at the load side must begin only for t greater than or equal to Td, right. So we now have an incident voltage. what we want to do is to find out what would be the reflected voltage, and then add the incident and the reflected voltage in order to calculate voltage at the load and voltage at any point on the transmission line. We can do so if we remember that the line voltage consists of incident plus reflected voltage, line current consists of incident current and the reflected current, and there is a relationship between these quantities with respect to the load voltage. What is the relationship? Let us look at that relationship now. So at T equal to TD and thereafter, we know that line voltage that we considered, let us call this as some V of L comma T, where V of L comma T will be the total voltage. I have dropped the subscript line here into this one, I have dropped the subscript line here, and this is the load side voltage, correct. So V of L comma T, which is the load voltage, or this would be the line voltage evaluated at the load terminal, must be equal to the load voltage VL of T, and this is further equal to V plus of T, which is at the load side, okay. So let us, this one V plus of the load side plus V minus of the load side, okay. The plus and minus of course indicating the forward and backward travelling waves. Similarly, Z0 times IL of T, I have just moved Z0 onto the left hand side of IL of T just to avoid writing a fraction here, but you can clearly see that this is given by Z0 IL of T is given by minus V plus minus V minus, all evaluated at the load side, correct. This of course is the line current I of L comma T. So this is the line voltage, this is the line current, this is the load voltage, this is the load current, and these quantities are obviously equal when you evaluate this one at the load side, and of course they are equal to these right hand side quantities. Let us now add both equations and eliminate V minus of L comma T. Although our idea is to find V minus, let us now follow this procedure. Let us add, eliminate. What we will do is we will find one unknown, from that unknown we will find out the reflected voltage. So adding these two, we get VL of T plus Z0 IL of T, that must be equal to 2V plus L comma T. Is there a way to understand this equation better? Well, this is an example of a KVL type of an equation, right. So here you have a source which has an amplitude of 2, or which has a this one of 2 V plus of L comma T. If we remember further that V plus of LT is nothing but V0 by 2 U of T minus TD, because we are considering this one at T equal to TD, correct. So beyond that only your voltage has arrived at the load side, and hence from the load side it will be reflected. So because of this one way propagation delay, V plus the incident voltage at the load side would be equal to the step voltage of amplitude V0 by 2 that has been delayed by TD. So go back to this one. So this must be equal to Z0, let us say the current flowing through this one must be IL of T, right, and then you must have a load voltage which is VL of T. What is the load here? It is the inductor that we have considered. Does this, if by applying KVL you can show that this equation is actually represented by this. Further, very curiously, this value of 2 V plus of L comma T is actually the open circuit voltage, correct, is open circuit voltage at the transmission line output, correct, because you take the transmission line over here and then connect this RG to whatever the VG that you wanted to connect here, right. If you leave this one open circuit, then clearly gamma L will be equal to plus 1, which implies the total line voltage evaluated at L comma T must be equal to the incident voltage, but because gamma L is plus 1, the reflected voltage will also be the same. So it would be V plus of L comma T, which is equal to 2V plus L comma T, okay. And further, if I remove this VG, that is if I short circuit this VG and look from this side what is the input impedance over here, I see that the input impedance for a open circuited load for this one would actually be equal to Z0, or rather I should look at the input impedance from this side. So I see that the input impedance in looking at this point will be equal to Z0, because this RG is now equal to Z0. So essentially what we have written, this portion of the circuit, okay. So this portion of the circuit that we have written here in this green color thing that I have written in that box, that is actually the Thevenin equivalent of a open circuited transmission line with Rg equal to Z0. Okay, so this is the open circuited equivalent circuit, and from there we are simply attaching the load and then proceeding now to find out the load voltage and the line current. How do I do that? Well, this is an inductor. What is the relationship for an inductor in terms of the voltage and the current? For an inductor, we remember that if VL is the voltage across it, IL is the current through it, and the inductor has a value of L, inductance, measured in Henry, then the voltage VL will be equal to L dIL by dt. So I can substitute this expression VL of t, IL of t. So I can substitute this expression into this equation, right, and then try to find out VL. Because this is unknown, this can be expressed in terms of VL of t or its derivative of that one as such. This is known to us because this is the input that we have considered. So this is known to us, right. So this 2V plus L of t is actually known because V plus the incident voltage at the load is given to us V0 by 2 U of t minus Td. So let us do that one. So we substitute this as L dIL by dt plus Z0 IL. Of course these are all functions of time. I don't have to specify small l which denotes the load here because this capital L itself is denoting the load. So this must be equal to V0 U of t minus Td. This problem is very well known to you. This is actually a step response of an RL circuit, right. So a step response of an RL circuit, except that the step is applied at t equal to Td. Instead of the usual t equal to 0, it is now applied at t equal to Td, but if you simply move the reference 0 to Td equal to 0, then the solution of this one must be in the form of an exponential. Initially, what will be the response of the inductor if the inductor is not connected, if not charged initially? It will act like an open circuit. So which means initially there won't be any current. Finally the inductor will act like a short circuit for a DC voltage, which means the current would have gone to its maximum value. What is the maximum value of the current? V0 by Z0 will be the maximum value of the current. So in between it has to actually slowly build up to it with a time constant of L by Z0. Remember, for an RL circuit the time constant is given by L by R. So that's all. So you can go back to the differential equation, apply the boundary conditions, solve it, you can do all that, but the net result that you are going to obtain is fairly simple. From the physical arguments and from a previous experience, we can write IL of t as V0 by Z0, which is the final current, okay, to which it must charge exponentially with a time constant tau, where tau is equal to L by Z0. Does this equation make sense? Let us evaluate. At t equal to Td, e to the power minus t minus Td divided by tau will be equal to 1 because t equal to Td, so e exponential of 0 will be equal to 1, and therefore IL just when the step is arriving will be equal to 0. This clearly is the condition that we want because we had not charged the inductor before. Now when t minus Td tends to infinity, that is when you wait for sufficiently large amount of time, right, then what happens to this exponential? The exponential term e power minus t minus Td by tau will tend to 0, right. So it will simply drop off, and IL at infinity, that is in the steady state, will be equal to V0 by Z0. Okay, so the current eventually goes out to V0 by Z0. In between, how does this charging process look like? We are very familiar with this, the exponential. So initially you are starting at 0 and then you slowly go up, exponentially, or rather 1 minus exponentially with a time, the time constant of tau. So this is with respect to the time axis. This is the current IL of tau. So initially 0 to a final value of V0 by Z0. Now it is very easy for us to find out what is the load voltage. Load voltage is simply L dIL by dt. So differentiate the above expression, multiplied by L, you will get the load voltage. What would be the load voltage across the inductor here? So if you differentiate the above expression, you get V0 by Z0 1 by tau here. So I know that 1 by tau is Z0 by L. So this will cancel out to Z0 will cancel from numerator and denominator, L will cancel, and you should get this as V0, and of course there is an exponential, right? So I did not write the exponential, which is written here, T minus Td divided by tau. It's the same process. Initially, because the inductor is acting like an open circuit, the full voltage appears across the inductor, okay, and no current will be flowing in that loop. But from that value it will keep on dropping, eventually going to 0. So if you sketch the load voltage, okay, this is the load voltage that I am sketching. Initially we begin with V0. The two graphs that we have drawn, they are all right, except that these graphs should have begun at Td and this graph should begin at, or rather exponentially going down with a value of V0. So it begins at V0 and then gradually or eventually goes out to 0 here. So this is the load voltage, but what is my reflected voltage? If I ask you what is V minus, so minus is in the numerator, is a superscript, so it is V minus L comma T, that is the reflected voltage at the load. What would it be? It's very easy to find out. Remember, VL of T is the load voltage, which is given by V0 U T minus Td. Do you remember where this is coming from? I hope you remember this. My plus V minus of L comma T. So solving this equation, you obtain for the reflected voltage V0 e to the power minus T minus Td by tau minus half times U of T minus Td. Okay, so this expression will start at T equal to Td and then go all the way up to infinity. How does that look? We can actually sketch that one. So let us sketch that right here. So the reflected voltage at the load, so this is the reflected voltage at the load, begins at T equal to Td with a value of, so this would be 1, the exponential factor will be 1, and 1 minus half will be equal to half times U0, right? So it will actually start at V0 by 2, and what will happen eventually when T minus Td becomes much larger than tau, this goes off to 0 and then you get minus half times V0. So eventually it would have dropped down to minus half V0, okay. So this is the reflected voltage that actually starts to propagate in the backward towards the generator. So at the source, this reflected voltage would actually propagate and add to the outgoing voltage. So outgoing voltage, if I now were to plot the total generator voltage at Z equal to 0, I know that I am already sending V0 by 2. This V0 by 2 is the initial V1 plus that we had, right? So this V0 by 2 is traveling at a time of 2 time delay. The reflected voltage, which would be of this form, which started off in this way at time t equal to Td, would now arrive after a time delay of Td seconds, and therefore it would initially add up. So you will initially see a jump in the voltage of V0 by 2, and eventually this value, because this is minus V0 by 2 is the final value here, that gets added to the outgoing voltage of V0 by 2, and therefore you will see that this drops off considerably. Let me redraw that one here. So this is the time at 2D, up to 2D you have V0 by 2 amplitude at the generator side, then there is a jump of V0 by 2, so that the value here is actually equal to V0, okay, and then it slowly drops off, eventually going down to 0. So you see, this is the voltage that you see at the input terminals of the transmission line. So this completes our problem with respect to the inductor. Let us now look at the problem with the capacitor. What I will do is I will go over or sketch the solution rather quickly, and I will leave the steps for you to verify, okay. So in place of an inductor, if I put a capacitor, what would happen? The equivalent circuit won't change, okay. The equivalent circuit that I had in mind earlier or derived earlier is still 2V plus of L comma T, which is equal to V0 U T minus Td, which we have already seen, connected through the characteristic impedance of Z0, now connected to a capacitor, okay. Across the capacitor is the load voltage, and through the capacitor is the load current. The corresponding differential equation must now be written in terms of the load voltage. Why? Because if this is the load voltage, the current through this branch, current through Z0, will be given by 2V plus the voltage on the left side minus VL of t divided by Z0, and this current must then be equal to the current through the capacitor. Current through the capacitor is C dVL of t by dt. So this is the equation that you need to solve with the known voltage here, known voltage waveform here. Solve for the voltage VL, and you can see this after solving, this will again be exponential, right? It would be 2V plus 1 minus e power minus t minus td by tau times u of t minus td. Okay, why is this making sense? It makes sense because capacitor, which is initially uncharged, will appear like a dead short here. It will appear like a short circuit which carries the entire current, but the load voltage will be equal to 0. The capacitor voltage initially is 0, and eventually as we go along, with respect to time, it will be completely charged to the voltage of V0. So if I quickly sketch what will be VL of t, I start at TD with 0 voltage and then eventually go out to V0. Okay, from the same equation VL, you can find out what would be V minus. I will not derive it, but I will leave this as an exercise. So V minus at the load side would be something like this. So at TD you start with an amplitude of minus V0 by 2 and then gradually keep going all the way up to V0 by 2. Okay, if you now combine the incident and the reflected voltages, you can draw the voltage at the load side, and that load voltage will be initially an amplitude of V0 by 2 step is propagating, and when you receive now a voltage of the form this way, initially negative and then going towards positive, that step would be equal such that the equal in magnitude but opposite in sign to V0 by 2, such that it will pull down the voltage completely to 0 at this point and then begins to rise to a final or an asymptotic value of V0. So this is how you can actually distinguish, if you were monitoring the voltages at the input terminals of the transmission line, distinguish between an inductor and a capacitor. In fact, an instrument that does so is called as a time domain reflectometer, which is a study for our next module. Thank you very much.